Yeah, I hope you can hear my voice.
Yes, sir.
Okay, good. So, alkyl halides and aryl halides, okay. What or halogen derivatives, or you may call them as both are same thing, okay. Haloalkane or haloarenes, right? What are aryl groups? Yeah, tell me quickly. What are aryl groups? What do you mean by aryl? As the name is indicating, Krishna. What do you understand by aryl word?
Sir, I think it is aromatic
Yeah,
group substituent.
general, yeah, good. Yeah, aromatic substituent is known as aryl group. Okay, it can be normally it is most commonly it is benzene. Okay, but doesn't mean that always it has to be benzene. It can be some other aromatic ring like naphthalene also. Okay, but the most common is benzene out of all those. So aryl or haloalkane, alkane or haloarene, arene is that aromatic group. Okay, so both or halogen derivatives of hydrocarbons or the compounds of carbon and hydrogen. So both, all these names are same. The halogen indicates it can be fluoride, chloride, bromide, and iodide, right? But actually, the most important halogen which we have are fluoride and bromide, which are the most. Iodides are also very common, right? So we can have all these halides, and so let's start with the preparation. So tell me, how do we prepare them? So preparation is from alkanes. So the first and the foremost thing is alkane. How do we prepare them from alkanes? Tell me. What is the way to prepare them from alkanes? Yeah, Krishna.
Sir, in the presence of light.
Yeah. So what you will say? Alkanes actually. Yeah, you are correct. But you can say a common term, photohalogenation of alkanes. Okay. That's a as it is written over here. You can see the heading photohalogenation of alkanes. And what does this mean? It means you are attaching a halogen group in the presence of on an alkane in the presence of light. Okay, so you can see the light is mentioned. Normally you can take the heat also. Okay, but normally the light is mentioned over here. As you can see, that H nu represent light. Okay. Because you need to provide energy for the reaction to occur, and that energy is present either as heat or in the form of light of appropriate frequency. That H into nu is what? Can you tell me? What is that H nu? H nu is the energy of the photon of light. Okay. H is the Planck's constant. So it is generally written, it is sunlight also. But most importantly, it is UV light. Okay. So why UV light? Because UV light has more energy. So you need to give that light of appropriate energy, then only the reaction can occur. Otherwise, the reaction cannot occur. Suppose if you are not providing the light of appropriate frequency, then the bonds will not break, and definitely the reaction will not occur. And so you can see here the photochlorination, photobromination. Okay, you can do it multiple times as it is written in the third reaction. Okay, so the first time, actually, this is which type of reaction? Let me ask a very basic question. Is it an addition reaction? Is it a elimination reaction? Which type of reaction is it? Or is it a substitution reaction? Is it a rearrangement reaction? So this photohalogenation, Krishna, which you can see over here, is which type of reaction? Yeah.
Sir, displacement.
Yeah, it is displacement reaction. So it is known as substitution reaction. Good. Okay. So substitution reaction, and substitution can be electrophilic, nucleophilic, or free radical. So what do you mean by electrophilic, nucleophilic, or free radical? Just share it with me. If you don't know, not a problem. We will discuss each and everything. Yeah. Tell me.
Sir, electrophilic are those which are themselves negative and they have a liking for positive species.
Electrophile means electron-loving species. They are positive. They can be neutral or they can be positively charged. The charge is not the, but most probably they are positively charged because they want electron. Electron-loving species. They are electron-deficient species. They can be neutral also, but they need to have some empty orbital so that they can they can form bond with the electrons. Okay. Yeah. So this is electrophilic, not electrophilic, okay, because there is nothing electrophile which we have taken. What is nucleophile? Electrophilic species. Can you give me some example of electrophilic species? Electrophile, some common examples of electrophile. Vamsi.
Sir, any alkyl group?
Yeah, alkyl group is positive charge. The H plus is there. Any alkyl group is there. Okay, like R plus. General way is to write it like this: H plus, or we can have any positive. So neutral electrophiles are also possible, like AlCl3. We can accept electrons. PF3. Okay. Yeah. So these are electrophilic species, and nucleophilic species are nucleus level. So nucleus is positively charged. Actually, there are species which want to give their electrons lone pair, so they are called nucleophile. Can you give me some example of nucleophiles?
So OH minus.
OH minus, right? Or oxide ion? Yeah, correct.
Br minus.
Br minus, Cn minus. Yeah, and they can be neutral also, like ammonia, which doesn't have any negative charge, but it is having a pair of electrons which it can share readily with another atom, or water also. But neutral are definitely weak nucleophiles because they are stable, so that's why they are not desperate to attack. Okay, so nucleophilic substitution, but this is free radical substitution. Okay. So what are free radicals? So let me write over here the main important thing. This photohalogenation is free radical substitution reaction. Substitution as H is displaced by Cl. What do you mean by free radical substitution? Yeah, tell me. What are free radicals? Yeah, Krishna.
So they are species which readily react to form substitution reaction.
Yeah, but I need to be, you need, yeah, you are correct, but you need to be more specific. What is there in them? That's why should I call them radical? Yeah, the answer which you are given is correct, but I need you to be more precise, right? They have that unpaired electron. Okay.
Yes.
They have that single unpaired electron. That's, suppose if you take Cl minus, it is a nucleophile. Br minus is a nucleophile. But if you take an example of Cl with unpaired electron, it is just like a Cl atom, single Cl atom, which is having one unpaired electron. So that is radical. So Br radical. Okay. So this reaction, these are intermediates, definitely, because they are not stable. They do not have complete bond. So then they have a tendency to react and complete their bonds. So these are intermediates. Okay, these are called free radical intermediates. Okay, So that's why, so the reaction, the substitution is happening, but the substitution is happening not because of Cl minus. So it is not a nucleophilic, it is not an electrophilic substitution, because it is not happening because of the Cl plus, but it is happening because of the Cl radical. Okay, that's why it is called free radical substitution reaction. Okay, clear? Yeah. So ethane you can do, ethyl bromide, you can do it multiple times. Okay. So if you have one chlorine attached, it is called monochloro-derivative. If you have two chlorine attached, you have dichloro-derivative. You can have three chlorine attached. On methane, there is only one option of attaching two chlorine or three chlorine or four chlorine. Maximum in methane, you can have four chlorine attached. Okay, that will be CCl4, but you have only one option, right?
Yes, sir.
Why can't we have more options of attaching two chlorine or three chlorine? Why can't we attach two chlorine in two different ways on methane?
So because
Because
carbon is tetravalent,
the
and
carbon is tetravalent and there is only one carbon atom. Yeah, correct. There is only one carbon atom. So we can't, and both Cl should be on that same carbon atom only, a tetravalent. And that's why. So you can have chloroform, and if you if you do it multiple times, you can maximum you can go up to for methane. But for other higher alkane, you can put more. For example, in ethane, you can in ethane you can put more because there are 6 hydrogens. Okay, so you can have one monochloro derivative, you can have dichloro derivative, you can have trichloro derivative, tetra, penta, hexa. You can go up to 6. Okay, but if nothing is mentioned, you will put only one halogen. Okay. For example, this is cyclopentane and Cl2 is taken. And if you take light, just I put one chlorine. Okay, you can see over here. Cyclohexane is there and Br is there. Just I put one bromine. That's it. Okay. So I hope it is clear. So, and this is called photohalogenation reaction, and it is a best way to come out of alkane. If you are given alkane and if you want to do any other reaction, do photochlorination, photohalogenation, photochlorination or photobromination. Just keep it as a thumb rule of reactions. Okay. Now the thing is how the questions are asked. Okay. So questions actually there is a mechanism also. Question are asked on the mechanism. Mechanism actually is a way in which the reaction is happening, step-by-step explanation of the things which is happening inside the reaction. The equation doesn't depict all those things. Okay. So as I told you, this is a free radical mechanism. So first I told you it is a photohalogenation. You put some light of appropriate frequency, which is generally UV light. Okay. If someone asks you, you can answer it. So that gives some energy, and that breaks the bond of this Cl. Okay, so you can see these half arrows. Okay, these are known as barbed arrows, right?
yes, sir.
So actually this is you could give some energy, and that Cl atom, both the Cl atom get separated from one another. Okay. Now the thing is, there are two electrons. How the two electrons are going to get separated? That's the thing. So do the one Cl will take both the electron, or how? So because both are Cl, both have same electronegativity, they both will carry one electron, take away one electron. So that's how free radicals are in this reaction. And this is a start of the reaction. That's why it is called initiation step. It always require energy. Okay. Here.
Yes, sir.
Right. So that is very, very important. So now these Cl radical, what they will do, because they are very unstable and they do not have complete bond, so they will have tendency to go and attack on other species and snatch away some atoms so that they can complete their bond. So who is taken along with this Cl radical? Methane is taken. Okay, so what this Cl radical will go and get attached to hydrogen. Okay, and that's how. So it will take only hydrogen radical. Okay, hydrogen radical is not formed. That's a very important thing, because many questions ask it. in many questions it is asked. Do the hydrogen radicals get separated? No. The Cl radical just collide with a methane. Okay, join itself to the hydrogen, and the hydrogen is taken away by the Cl, and you get HCl. And what is left behind on the CH3? You have CH3 radical, methyl radical. So the problem which was of chlorine, now it is on the CH3 group, okay, methyl radical. Now what this methyl radical is going to do? Now it is unstable, okay, it is not going to stay as it is. Their lifetimes are very short, okay, because of the incomplete bond. So this methyl radical is going to attack on chlorine. Okay. So chlorine, CH3Cl and Cl radical will again form, and this Cl radical is again will go and attack on some. You can again come back to step number 2. It can again attack on a fresh methane molecule, and that's how you can have products, right? But it doesn't mean that the reaction. So these steps are known as chain propagation step. So in chain propagation step, one radical. So whatever I am telling you is asked, okay, all the time. Be careful, okay. These are asked as statements. So in chain propagation reaction, the radicals which are formed will go and attack on another atoms, neutral atom. They snatch some they will go and attack on neutral molecules, and they will snatch away some atom out of those molecules, okay. And some new radicals will form. The new radicals will again attack on some another molecules, and that's how the product. This is the product as well. This is the product one. Okay, I hope it is clear, right?
Yes, sir.
Any doubt in this?
No, sir.
Okay. So, but it this doesn't mean that it can keep on continuing on its own for a long time, because it may happen that suppose two radicals both are unstable, they may come and join one another. What will happen? Cl2 will form, as you can see, or two methyl radicals can combine with one another. Okay, and this is just the reverse of initiation step. These steps are known as termination steps. Okay, chain termination steps, right? And they are responsible for the decrease in number of radicals, because the radicals join together, okay, and they form something which is neutral. Okay, so this is the mechanism, right? And yeah, so what is the, let me ask you one thing which is asked all the time. Can you compare the rate of chlorination, bromination, or iodination? Can you compare the rates of these photohalogenation reactions? Yeah.
Sir, according to their degree, right? Primary, secondary, and tertiary.
Yeah. Pardon?
No, sir. The comparison is taken place according to the degree, right?
According, yeah. Suppose if I ask you, suppose if I ask you that I take methane, okay, and if I ask you, I carry out 4 reactions in different containers. Methane, I can react with fluorine, bromine, and iodine in 4 different containers. Okay. Right?
Yes.
So, which reaction will occur most quickly?
Sir, iodine, because it is more reactive than the others.
Iodine. Iodine. Okay, let me give you some data. Okay, the bond energies. First of all, bond energies. F2, Cl2, Br2, and I2. What is the order of bond energy, and how you are saying that iodine is most reactive?
So the iodine radical will be reactive, right? When compared to fluorine, chlorine, and bromine.
How you are saying that? What makes you think?
So reactivity increases down the group.
Reactivity increases down the group. That is for alkali metals. It's not for halogens. Halogens, it is reverse. Fluorination is most reactive and iodination is very less reactive. Because metals lose electrons. Okay, and they can lose electrons if they are bigger, because the electrons will be farther. So if the metals are bigger, as you move down, they become bigger and bigger, and they can lose electrons more and more easily. And that's why the reactivity of metals increases down the group. But for non-metals, they need to accept the electrons. The non-metal, the trend is reversed. They can accept electron if they are small. This is one thing. There are other factors also. I'm just telling, and there are exceptions also. Okay, I'm just telling you the basic outline. Okay, there are it can change. Okay, just I'm giving you a outline, because non-metals during the reaction they have a tendency to gain electron, and it is better if they are smaller. They can gain it more easily. They can hold that electron very easily, right?
Yes,
Yes.
sir. Yes, sir.
I hope this is clear. Yeah, okay, yeah. So this is clear now. So which step is endothermic? Which step is exothermic? Can you tell? So fluorination is most reactive. Then chlorination, then bromination, and iodination is least reactive. Okay. So what you were thinking, that is true for. Actually, that is true for metals. Okay. Clear? Which step is endothermic? Tell me.
So the initiation steps, sir, first one.
Yeah, that requires energy. That is endothermic. Okay. And which step is exothermic? Always exothermic. Tell me.
So the second step.
Second step is no, the third step. Actually, second step can be exo or endo, right? Because bond is forming and breaking also, so it depends actually. Okay. So it can be exo, but always exothermic is the last step, because always there is a bond formation. Bond formation, actually electron get attracted or joined together. Okay, they release it. Okay, this is, so delta H is negative. The delta H is positive. Right?
Yes, sir.
Now next thing, let's move to the next thing. So the another question which comes is, for example, we talked about the photohalogenation of methane. Okay, and in methane we have seen that, just a second, let me, I think there is a bar cut. Yeah, just hold for a second. Yeah, in methane we have seen that in methane, just there was only one carbon atom. Okay, and only one isomer was possible. Do you remember that? Only that was
Yes, sir.
only there was only one place where you can attach. Yeah, Krishna, can you hear me?
Yes, sir.
Okay, but so we discussed that. But in higher alkanes, actually, what is happening is and there are more number of carbon atoms. And because there are more number of carbon atom, the halogen can be attached at many places. So you need to tell me how many monochloro derivatives you get from each of how many different compounds, how many different structural isomer. If you put one chlorine, okay, monochloro derivative, you can see here. If you are allowed to put one chlorine on this structure, let's take example of A. So if you react with chlorine in the presence of sunlight and you attach one chlorine, okay, at how many different places you can attach that one chlorine? That you can tell me.
So 5 different types.
Yeah, 5. How you decided 5? Tell me. Yeah.
So the radical can react with 5. I mean, gets substituted at 5 different carbon
Yeah.
positions.
Yeah. This is pentane, right? That you agreed. Yeah. So there are 5 carbon atom. Yeah. And the chlorine can get attached to first carbon atom. It can get attached to second carbon atom. It can get attached to third carbon atom. It can get attached to fourth carbon atom, and it can get attached to the fifth carbon atom. Right? That's, I think you may be thinking in this way, right?
Yes, sir.
Okay. So partly you are correct. What you thought is correct. But now you need to think one more important thing. And that is, are they giving new products? Tell me.
No, sir. I think it's 3, sir, because we are repeating 2 again. Right?
Yeah. Exactly. Yeah. So you need to check. Okay. So 5 carbon means there are 5 carbon which can on chlorine can attach itself, or if someone give you monobromo derivative. So on the 5 carbon it can get attached. Okay. But are all 5 different? That you need to think. Okay. So are all different? If they are different, then only we are going to get a new product, right? But if they are same, so for example, this one and this one were same, this one and this one were same, and this. So you can, because this is symmetrical. Okay. From middle onwards, it is just the same as the right half is equal to the left half. Okay. So I hope you understood. So that it will not give 5 products. Okay. Just we will have 3 different products. Okay. Clear?
Yes, sir.
You were preparing for JEE, no? Or NEET?
JEE, sir.
Okay. Yeah. So this is a very common question which is asked. Okay. Everywhere. In JEE main, JEE advanced, every time. But they change the level of asking in JEE advanced. Okay. I will tell you how they ask. Right. But this is a preliminary question which is asked all the time. Okay. So what about this B option? Tell me.
So 4.
4. Just check it once more. How many different carbon are there? So you can mark the middle portion, okay, and check whether both the parts are same or not. Okay, so you can see the right half and left half across this line are same. Clear?
Yes, sir.
So this one and this one are same. This one and this one are also same. Okay, and these two are methyl groups. They are same actually. Okay, because they are connected to same methyl. And similarly, these two are also same. So how many different places the halogen can get attached?
So I think it's, oh yeah, it's 3, sir.
Yeah, 1, 2, and 3. Yeah, correct. So that's the way to think, right? Okay. And this was the question which has been asked in JEE mains many times, and it asked advanced also. Yeah. Tell me how many different. But this is not a symmetrical molecule. Some carbon are same and some are. What is the name of this? What is the IUPAC name of this compound?
So 2-methyl pentane.
Yeah, 2-methyl pentane. So how many monochloro derivative means, that is also very important. Okay, because I'm asking only one. Okay. So how many monochloro derivatives are possible? For this, yeah, just write.
Sir, I think it's 5.
Yeah, correct. You are right. Okay. What about D? Yeah, what about D?
Sir, 3.
D cyclohexane. Yeah. So there are 6 carbon atoms. Are all of them different or same? Just tell me. They are different or same? Can you differentiate between? Can you make out whether this is the upper carbon and this carbon and this carbon, or that one, this one, and they are different? Is there a way to make out, or they are all same?
So not all carbons are same because there's a double bond between them in
No, no, double bond is not there. All are single bond. All are single bond. Now tell me.
so it will be 1.
Yeah, only one. Right, correct. Okay, because all are 6 carbon and they are same. Okay, so it will be 1. So likewise, we can have it. This is the final answer. Just check it and tell me. Have you understood? All of them. This is the most common question asked in all the examinations. And it has been asked many times in JEE main, JEE advanced. Clear? I hope it is clear.
Sir, one doubt, sir. In E
Yeah.
also, like all are single bonds, right?
Yeah, single bonds. E also all are single bonds. Yeah.
So then why are they considering 5, sir?
So you can start from here. You can take this one, this one, this one, this one, and beyond this, they are all same. Okay.
Okay, sir.
Yeah, because it is the other side is just the repetition of the right half is just the repetition of the left half. Okay. And what about this one? The last one, F.
Yes, I got it.
Yeah, good. So yeah, this is a very, very important question, and this is the next question which has been asked in JEE Mains, DYQ, previous year questions. So actually, just I told you that whenever you are doing halogenation, you can attach 1, 2, 3 chlorine or 4 chlorine. Okay. So but you want to attach only 1 chlorine, as you can see over here, right?
Yes,
Here.
sir.
So when can you maximize the yield of that monochloro derivative? What are the reaction conditions you need to take? And the A, B, C, D options have that reaction conditions in them. Yeah. What could be the right answer?
So I think it's C.
C, yeah, how you are telling it C? Yeah, your attempt is good. You need light. Okay, B option is absolutely incorrect. Why?
So the reaction won't. I think it won't take place in the presence of
Yeah,
without the
reaction.
presence of light.
Yeah. Reaction won't happen. Yeah. Good. So, but why then C? Yeah. Okay. So think once more. Actually, suppose if you have chlorine in excess. Excess means you understood now. What do you mean by excess?
It's a large amount.
Large amount. Larger than whatever is needed. So what is going to happen? Everywhere, all the hydrogen ultimately will be displaced by chlorine. Got it?
Yes, sir.
So what you will end up with, if you take C option, you will end up with what?
So I think CCl4.
Yeah, it is because it is similar to that only, but it is ethane, no? So C2H6 only, you will write C2Cl6. Right?
Yes, sir.
You will end up with this. Okay, so what you need to do is, how can you make sure that only one chlorine get attached?
So option D.
Option D, but option D is just an approximate option because no quantity is mentioned. Think more. Suppose if everywhere you have ethane around you, so what are the chances with whom chlorine can react? Each chlorine can, radicals, once it is formed, it can react with ethane. Okay?
Yes, sir.
Because if everywhere you have ethane, so each ethane at maximum will attach to one chlorine because you have many ethane. You have taken ethane in excess. Okay?
Yes, sir.
Here. So
Yes, sir.
the right answer is going to be option A. Okay, but if you take Cl2 in excess, all the hydrogen will be replaced. But if you take alkane in excess, so note it down. If you take alkane in excess, which is going to be the major product, the monochloro derivative, is going to be the major product. Clear?
Yes, sir.
So this is a very important question, previous year JEE question. So I hope you understood it. So A option is the right answer. Now the next question, you already answered it. Just tell me quickly. Similar question we already did in that table. Yeah. Yeah. So this is the question which was asked in JEE. Okay, this is
So I
also,
think
but
it's 4.
yeah, correct. It's 4, but same way you need to answer. It's 4. Okay, and yeah. So let's move to the some important part. So this we discuss rate of photohalogenesis. Right? Is it clear? This
Yes, sir.
we discussed. So fluorination actually is, fluorine is very reactive and it is uncontrollable. Means you can't stop it once it's started. Okay, and you can't control it. It become uncontrollable reaction. So direct fluorination is never carried out. It is carried out by some other means which is known as Schwartz reaction. Okay, I will explain it to you. Schwartz reaction. Uh, what you do is you prepare, suppose methane is there. You don't go for fluorination directly. What is the reason? What's the reason? Yeah. Yeah, Vamsi. Tell me.
No, sir, I'm not sure.
Actually, it is because fluorine makes a very strong bond and it evolves a lot of heat. And if it evolves a lot of heat, what is going to happen? You will not be able to control the reaction. Okay.
Yes.
Because the heat is going to make the reaction more vigorous, right? And if it is becoming more vigorous, you can't control it. Okay. Right?
Yes,
So
sir.
that's why you don't do this is the direct chlorination, you don't do it. So how you do? You do chlorination or bromination. So if you want to prepare this, what you take CH3Br or CH3Cl, okay, and you react it with AgF or Hg2F2. So it's a displacement reaction in which the fluorine displaces Br. Not direct photohalogenation, indirect. Is it clear?
Yes, sir.
Okay, so this is actually a very important reaction. Chlorination. So fluorination is not carried out directly because it is uncontrollable, highly exothermic. So what you do? So this reaction is known as Schwartz reaction. You need to know the name also. Okay. So this is Schwartz reaction, and Schwartz reaction is actually you prepare fluoride not by directly reacting with fluorine. Instead, you prepare alkyl bromide or alkyl chloride. Then you substitute that bromide or chloride by fluoride. Is it clear?
Yes, sir.
So I hope it is clear. Very important. Schwartz. The name is also very important. You need to remember it. Okay. Where? So in the for iodination, it is actually just the opposite case. So what is the case with iodination? Tell me. What do you think? Yeah. Yeah,
So
Krishna. Yeah.
yeah, we do it with HI, sir.
No, actually we take iodine. We take I2. But the problem is the reaction doesn't happen. Okay. It stops in between. So if you take methane, methane is CH3. Okay. And suppose if you react it with I2 in the presence of light, and you think that you will get just like what you observed in chlorination. If you think that in iodination something will happen similar, but to our surprise, the reaction doesn't proceed. It remains toward the reactant side only. Means what? Means whatever the reactants which you have taken, they are going to remain unused, unconsumed, right?
Yes, sir.
They will not form product. Means what? How should I say this? I should say this reaction is reversible. Means it is not happening. Okay. Why? Because iodine is least reactive. It breaks very easily with the help of sunlight. But simply breaking of iodine will not lead to the completion of reaction, as we have seen. Iodine radical, if it forms, it need to go and attack on the carbon, then only it can form a bond. Right?
Yes, sir.
But if the iodine radical is very large, it is iodine, can you tell me from which period is it iodine? Yeah, can you tell me the period? Yeah,
So fifth period.
yeah, it's fifth period. Okay, so it is a very large. So suppose if you we can write it like this. Okay, we can make that unpaired electron as dot. Okay. But the dot is actually very large orbital. Okay, it doesn't form bond easily. It is spread out over the huge atom. Okay, so that's why iodine is very less reactive. It can't go and react on with methane. So fluorination has some other problems. It was uncontrollable. Once it started, you can't control it. Iodination is the other extreme of the problems. If you have iodine, the reaction will not complete. So what is the solution? So the solution, there are two solutions. Okay, one is written over here. Another solution you can tell me, which is not written here. You can tell me that solution. Okay, and that is, suppose if a reaction is not proceeding in the forward direction, how you are going to shift that equilibrium forcefully in the forward direction? Tell me. Any idea? In class 11th, you might have studied. Yeah.
So we add a reactant which can easily react.
Yeah. Good. So if you increase the concentration of reactant, the reaction is pushed in the forward direction. Lee Chatterton principle. Or if you remove the product, if the products are getting removed from the reaction mixture, so automatically the reaction will be forced to move in the forward direction. If you add reactant more and more, they will react and they will form product. So there are two ways. Okay, so that what you may have studied in class 11 chemical equilibrium chapter. Okay, so if not, if you forgot, we can have more classes and you can coordinate. Okay, so here also we will apply the same trick. What we will do, we will do it. One solution is we will do it in the presence of oxidizing agent. The oxidizing agent will consume the HI. Okay, so if HI is removed, so one of the product is continuously being removed, so the reaction will move in the forward direction. Is it clear?
Yes, sir.
So iodination is not carried out directly because the reaction doesn't happen, it is reversible. First point. Suppose if someone say no, we need to do the iodination only, how we need to do it? You will say take some oxidizing agent like HNO3, HGO along with this reaction so that they can eat away HI. And if they can eat away HI, the reaction will be forced to move in the forward direction. Okay, right? The next thing is there is one more solution by displacement that is called Fingersteen reaction. Just similar to Schwarz, but Schwarz is the replacement of the halogen by F. Fingersteen is replacement of halogen by I. So we can get CH3Br or CH3Cl easily because they don't have that problems which we have seen in fluorine and iodine. Okay, they can form by direct photohalogenation. So if they can form, take it. And then iodine, because you can't attach it directly, use NEI in the presence of acetone as a solvent. Where do you see acetone? Yeah, tell me.
Sir, can you repeat?
Where do you use acetone? This is a solvent for mixing. Where do you use acetone? Have you heard of it, acetone?
Yes, sir.
Yeah, it is used in nail polish remover. And it is a good solvent actually. It is also used when there is a paint going on wooden things. It is used to remove the marks of the paint. Okay, it can dissolve. Okay, so acetone is a solvent because if a chemical reaction is happening, you need to put something to dissolve two components together, and acetone is a solvent. And the how you are going to put I, that was the main question, and the answer was that put NaIs in mixed into acetone and take some bromide or chloride. The I minus is going to come and join to the carbon, and during this process the Br minus is going to come out as a leaving group, and that's how you can have this, right? I hope it is clear.
Yes, sir.
So CHCI plus NEA, this is known as Fingersteen reaction. So for iodination we discussed 2 points. Directly it was difficult to complete, so we can take some oxidizing agent that will help the reaction to occur more easily, or we can do chlorination or bromination, and then we can put NaI. That NaI is more soluble in acetone. That's why the acetone is taken. And these are less soluble, Br and chlor. So Br will come because it is less soluble, it is going to come out, and I is going to attach itself. Is it clear? And that's how we are going to do this reaction. This is very important because a lot of questions are asked on this. Okay. All the point, do keep this in mind. Okay. So this is what I told you just now. Okay. Just go through it. It is very famous thing. Schwarz reaction is replacement of bromide or chloride by fluorine by taking AgF or Ag2F2. Iodination is reversible, so it is not carried out directly. So you put iodine by mixing in NAI with acetone and reacting it with your alkyl halide, which is having bromine or chlorine. I will displace bromine or chlorine, right? And this reaction, you also need to remember the name, because they ask what is the reagent for Fingersteen and all. Like they ask, okay. And suppose if we talk now, so if someone tell us to do photohalogenation, on our own we are not going to do chlorination because it has problems. On our own we are not going to do iodination because again it has problems. So on our own, if someone says us to do some photohalogenation, we are going to use chlorination and bromination. Okay. But chlorination and bromination, we need to be more specific. Okay. So what is written over here? Can you read it for me? This is a very, very important. Yeah. Yeah, Krishna.
Yes, sir. Chlorination is more reactive and less selective. Bromination is less reactive, more selective.
Yeah, what it means. Why I have written this here. Suppose if we are hungry, if we reach home and we are hungry, so whatever the food your mom has prepared, you will eat. Okay, without complaining. But suppose if we are full, then we become very fussy, right?
Yes, sir.
So then actually we say, okay, we will not eat this or we will not eat that. Okay. So same is the way we can explain this statement. So chlorine is very reactive. It can attach itself to any carbon, remove any hydrogen, and it can attach itself to any hydrogen in this given alkane. In the given alkane, okay. Whatever the alkane is given, you can put chlorine anywhere. But bromine is less reactive. It means what? It means it is more selective. If it is less reactive, so it's going to react only with those hydrogens which are more reactive, which can break very easily. Okay, so I should say it is more selective in nature, right?
Yes, sir.
Have you understood? So, and how can you decide that some hydrogen can come out easily or not easily? How will you decide the energies of CH bond? Any idea about this?
Sir, I didn't
Yeah.
get your questions.
How the bromine judge which hydrogen can be broken or taken away most easily? How the bromine judges? How the bromine, because why the bromine is more selective means it can attach itself to. Okay, I will tell you the selectivity. Selectivity means the bromine is having more tendency to attach itself to tertiary carbon, then secondary, and then primary. Tertiary carbon, you know what is tertiary,
Yes, sir.
which is connected to 3. So bromine can break hydrogen from tertiary carbon most easily, followed by secondary carbon and followed by primary. Okay, so how bromine knows that this hydrogen is tertiary? What makes bromine think and decide that this is tertiary hydrogen? Why bromine breaks only tertiary hydrogen most easily? Tell me. It's the reactivity of hydrogen. Okay, it's the bond energy of the hydrogens. Okay, the hydrogen which can break most easily is tertiary, followed by secondary and followed by primary. But why tertiary hydrogen can break most easily? The answer lies in the radical which is formed after abstraction of tertiary hydrogen. Suppose if Br radical comes and breaks away the hydrogen, takes away the hydrogen radical along with it. What is left behind on the carbon? Carbon radical. Okay. That carbon radical, you need to look at that carbon radical because hydrogens all are same. Whether it is the hydrogen of methane or ethane, or whether it is the hydrogen of propane or butane, okay, or whether it is the hydrogen of 2-methyl propane, all hydrogens are same. But how come the some hydrogens can be abstracted? Some hydrogen mean tertiary hydrogen. How come the tertiary hydrogen can be abstracted very easily as compared to secondary and primary? Okay, the answer not lies in the hydrogen, but it lies in the radical which is formed after the abstraction of hydrogen. Okay, is it clear?
Yes, sir.
So radical is formed. So you need to look at the stability of the radical. So what are the factors which stabilize radical? Can you tell me? Do you remember?
So the substituent groups are attached to the radical.
Yeah. So more substituted carbon, if it is there, it can form a stable radical. Like this is tertiary, 3 substituent, and these will stabilize the radical by giving away its own electron. Okay, followed by secondary, because radical is an electron deficient species. Okay, so if there are groups which can help the radical to form by giving their electron density, it can form most easily. And primary radical, methyl radical, right? So I hope it is clear, right?
Yes, sir.
So this is how it is happening. So, but there are some radicals which are not tertiary but very stable. What are those radicals? Yeah, tell me. Which are more stable than tertiary radicals? Yeah.
Allyl
What
radical.
are allyl? Allyl and
Benzyl.
benzylic radical. What do you mean by benzyl?
The
What?
benzene group is attached, substituent group is
Yeah,
attached to the main.
yeah. Yeah, the carbon which is directly outside the benzene, not the carbon of the benzene, but which is outside, just connected to the benzene, is the benzylic carbon atom. And that's where the hydrogen, the benzylic hydrogen, can be abstracted most easily with least by putting least amount of efforts. Then the allyl, you can see over here. But why? So if you abstract this benzylic hydrogen, you will end up with benzylic radical, and similarly, if you abstract this allylic hydrogen, you will end up with allylic radical. But why they can be abstracted most easily? What is the reason? Yeah.
So you're like asking why is it stable?
Yeah, why it is stable? Yeah, because yeah, you can tell me.
So due to the nature of the substituent group, which is more heavier, makes it more stable.
Yeah, good. But you need to be more precise. I need to hear that word, one word. It is because of the nature of the
So
substituent.
bulky.
No, bulky will mean maybe a very general term. Actually, the substituent is having loose electrons, pi electrons. Okay. Suppose this is the unpaired electron. It is there in the p or y. And allylic radical is just near to this carbon which bears the radical, there is a double bond sitting near to it. Okay, that also has p
Yes.
orbitals. So what happens is this p orbital and the double p orbital of the double bond being neighbor, they overlap and they're overlapping somewhat, and that electron density of that unpaired electron mixed up with the electron density of the pi. Okay, and so it becomes stable. That's all. If the electron density get mixed up, the energy decreases, potential energy decreases. Okay, so it has been shown that it can come on this carbon or this carbon. How it is possible? Because the pi, and this phenomenon is known as resonance. Okay, right? It is the delocalization of loose electrons, like lone pair, free radicals, or pi electrons. Okay, that's why it is there. Similarly, if you have this benzylic radical, that also can do resonance because it is just same as that of the allylic radical, but just two more double bond in the ring, so it can get into the ring. That's how it can become more stable. And if it can become stable, it can form easily. Suppose if you are breaking away the H radical, and if something which is forming is highly unstable, it will have more energy, so it will not form easily. But if something is there which can form very easily, because it is very stable, it can, that's why it can form very easily. Okay, right? So I hope this is clear. So, but who can recognize the stability of radical? Is it the chlorine or bromine? Yeah, tell me, Vamsi.
So
Who can
bromine.
recognize? It's the bromine being more selective. Yeah. So bromination will occur more easily at tertiary, then secondary, then primary. Chlorine doesn't recognize it much, okay, because it is very reactive. If it's itself very reactive, then how it is going to make out? It doesn't matter whether it is abstracting tertiary hydrogen, secondary or primary. It doesn't matter much for chlorine, but it matters much for bromine, right? So, and how now it is going to affect our product? That's the main question. So we have discussed the underlying reason for the selectivity and what is selectivity. But now the main thing which is required for solving the questions and which is required for the identification of major product. So identify the major product in these reactions. So suppose if someone asks you how many products can form, you will write all the possibilities. Okay, be very, very careful. But if someone asks you, what is a major product, then you are not going to write all the possibilities, right? You will just mention one product which will form in the maximum amount. Okay. So tell me which is the major product for this reaction. Yeah, Vamsi.
So bromine will be attached to the second carbon or the third carbon. So that will be the major
Yeah.
product.
Yes, there are two outermost carbon, those are primary. Okay, which are CH3. Okay, and there are two carbon in the middle, which are CH2. They are secondary because each carbon is connected to the carbon. So which hydrogen can be abstracted most easily by bromine? The activity order was tertiary, followed by secondary, followed by primary.
So secondary, sir.
Yeah, secondary can be abstracted most easily. So, and bromine being very selective, So this is the major product, 2-bromobutane, right? So that's the main use and the main application of what all we discussed, and the reactivity versus selectivity principle. Is it clear?
Yes, sir.
Okay, good. Now the next thing is, this is the other product. What is the major product? This is a very big molecule. Okay, a lot of carbon atoms are there, but that doesn't mean that the bromine will, all the products will form in equal amount. And because the question is asking only the major products, so you need to say only major. Right. Tell me.
Sir, it will attach on the tertiary carbon.
Yeah. What will be the IUPAC name of that? IUPAC name is also there. So I'm writing it in bond line representation. There are two methods. Okay. So this is the product. So it is hexane. This is the main chain. Hexane, on second carbon there are two groups, 2-bromo, 2-methyl. Okay. Methyl are there on the fifth carbon also. But I started counting from this bromine side because
Yes, sir.
it come before. If the substituents are same, you need to look at the alphabetical sequence. Clear?
Yes, sir.
Methyl, same. Clear?
Yes.
And now comes this benzylic one. Yeah.
Sir, in the tertiary carbon, sir.
But this doesn't have any tertiary carbon.
Sir, at the junctions, like in between CH2, CH3, and
Yeah. So this is the carbon atom which is just connected outside the benzene. So this is benzylic. Okay. So benzylic carbon. Is it clear? So here you can see the main distribution of the products. This is the actual thing which is happening with the numbers to support our answer. Right?
Yes, sir.
Now let's do one question. This is same simple question. You did it earlier also.
Sir, option C.
Option C. The 2-bromo-2-methyl butane. Correct. Good. That will be the right answer. And now the next thing. Okay. Now there is one more hurdle. Read this question. And I have, in order to highlight the difference. I have highlighted the statement in red. So total number of monobromo derivative, you already did this question. But yeah, now you need to tell me how many stereoisomers are forming. Getting it or not?
So stereoisomers.
What are stereoisomers? So first of all, okay, don't jump. No matter how difficult the question is, no matter how, whether it is from advanced, okay, I always say my students, it will be there in the inorganic also, okay. So I always say my students that don't jump directly to stereoisomers, which I will explain. First, write structural isomers, which can form. And because you are not going to write only the major product, because it is asking total number. Means you have to write all the products. So tell me first, write the structural isomers, what all products can form, then we will get into the stereoisomers. So always do follow this approach, you will never go wrong. While finding the number of isomers, okay, to follow this approach which I have shared with you. First, always write structural isomers. So how many structural isomers can form? Yeah, this you already know, the question which we did at the start.
So two.
Two, yeah. And what are the names? Yeah, correct. This is one bromobutane and the one is two bromobutane, which is the major product. But here I don't have to mention which is the major or minor because the question is just telling. Okay. Total products you need to answer. Okay. Right. So
Yes.
now stereoisomer. What do you think about stereo? What they are? Yeah, tell me.
So I think it is the halogen which is attached. I mean the isomers which have halogen at the last,
Hmm.
with like substituent group at the last.
So stereoisomers are type of isomers which have same connections, which have same sequence of bonds. Okay. They but they differ only with respect to 3D arrangement of the groups in space. Those isomers are called stereoisomers. So, for example, these two are not stereoisomers; these are structural isomers, and among structural they are positional. As you can see over here, that bromine is connected to one or two, and the sequence of bond is also changing. If you compare the molecule from the right half to the left half, or left half to the right half, you immediately in the first one you will encounter that the bromine is connected to the first carbon atom, but in the second one the bromine is connected to the second carbon atom, and there is a change in sequence of the bonds because bromine, whether it is connected to the first or second, that makes that changes the sequence of bonds, right? So if the sequence of bond is different, you can make out very clearly, very easily. You can just compare two molecules atom by atom. Okay. So such isomers are known as structural isomers. And these are positional isomers. Right? But if the position is same, the atoms are located at the same point, the connectivities and the bonds all are same. only the three-dimensional arrangement are different, then such isomers are known as stereoisomers. Is it clear? The definition.
Yes,
So
sir.
stereoisomers are those isomers which differ only with respect to the three-dimensional arrangement of groups in a space. And one stereoisomer you already studied in class 11th, and that was geometrical isomers. Geometrical isomerism, cis-trans isomerism, right? So if you have this, do you remember cis-trans, Krishna?
Yes, sir. Both the substance groups are on the same side.
Yeah, this is a type of stereoisomerism only, right? So because how they are stereoisomers, yeah, this is cis and this is trans. And why they are stereoisomers, we can prove very easily that both have same connections. So start from, you have methyl and hydrogen, you have carbon, you have double bond, you have carbon, you have methyl and hydrogen. Same thing is here also, methyl and hydrogen, carbon, double bond, carbon, methyl and hydrogen. So if you are comparing bond by bond, they are same. But that doesn't mean that there is no difference. The difference is there. But is the differences with respect to the connectivity? Now you have to be very specific. Or is it the difference with respect to the 3D arrangement? Yeah, tell me.
3D arrangement.
Yeah, it is the 3D arrangement in space. How these groups are aligned in space, that's what the difference is. And you can see over here that the two groups are on the same side or opposite side, okay? And this is actually the main difference, same side or opposite side, okay? So these are stereoisomers, and geometrical isomers are actually stereoisomers, right? Clear?
Yes, sir.
Okay, clear. So, but here we can't have geometrical isomerism because we don't have any double bond in the above question. You need to look for the different 3D arrangement and which bromo compound, one bromobutane or the two bromobutane, which can exhibit different 3D arrangement. Any idea, any guesses? Yeah. So stereoisomer, the definition is CN. The isomers which have same sequence of bond. Okay. But they differ only with respect to 3D arrangement of groups in space. And geometrical isomerism is one of the type of stereoisomerism. But the another type of stereoisomerism is optical isomers. Okay. So optical isomerism, we will look into it in more detail next time. Okay. So this you can tell me what do you think now can have different 3D arrangement? Just any guess from your side?
So the second product, which is the main product.
Yeah, second product. Yeah, good. And I have put an asterisk on the second carbon, this one, because this is the carbon which is connected to four different groups. Okay. And what are those four different groups? What are the four different groups connected to this carbon which is marked with a asterisk? Right. What are these four different groups? Bromine, you can see very clearly. There is one methyl group. There is one ethyl group. There is one hydrogen. Can you see it?
Yes, sir.
So four different groups. And the carbon atom which is connected to four different groups. Okay. No matter how far they are from that original carbon atom. But if the groups are even a slight difference will make them different. Suppose if you have hydrogen on one side and deuterium on another side, though both are hydrogen element, but they are isotopes.